So, there are other forms of work. So, what we are looking at initially was the PDV kind of work. So, what we looked at in between here with respect to the person falling or the apple falling, we are trying to look at gravitational work. Okay. So, the gravitational work is given in terms of mgh. So, h is the distance or height which the person is or object is falling, m is the mass, g is the acceleration due to gravity. So, this gives us the gravitational work. It is height over which the object has dropped. So, if the height was 1 meter, if the object, for example, this, if I brought it from this location up to this location by a distance of 1 meter. So, the work interaction for this object would be whatever is the mass into the acceleration due to gravity in this into this 1 meter. Okay. So, when this object is lowered, so its energy goes down and we see that work is it is giving out work. When this object is being raised, we see that the energy of this object increases and work is done onto the object. So, in raising the object, the work interaction for this object is negative. When lowering the object slowly in a fully resisted fashion, the work interaction for this object is positive. If we have, for example, a rotating shaft and the torque is T, if the shaft rotates by an angle of theta, then the shaft work is given as T into theta. Of course, what we are more familiar with is omega, which is the angular velocity of the shaft. So, 2 pi n would be omega, where n is the speed of the shaft in rotation revolutions per second. So, if you that would be omega, and if we multiply that by time, we get theta, and theta into the torque would be the shaft work when you have a rotating shaft. Similarly, we can look at other forms of work. So, when you have a steady current I which flows out of the system at a point A, re-enters at a point B. So, we have a closed circuit, we have a battery or something like that, and the voltage at A is higher than the voltage at B, then the system is said to do positive electrical work. So, the electrical power would be given as the current into the voltage, which is in joules per second or watts. The work would be this power into time. So, current into voltage into time. We also know from Ohm's law that we can write this as I square into R. So, the work would be given as I square RT or I into V into T and so on. Similarly, we can have work in other systems. For example, if you have a soap film, let us say I have some U-shaped object of this kind. I have a flexible, not exactly flexible, I have a movable pin. So, I have like a U-shaped metallic object. I have a soap film which is here, and one end of it there is a rod which can be moved. So, if I, for example, pull this rod, I am stretching this soap film which is sitting over here, or if I leave it, the soap film will bring this back closer and closer. So, that kind of work is because of the surface tension of a film. Similarly, if I have, for example, a balloon, I am blowing it, I can think of it as being like a membrane which is stretching. So, there is work interaction there. So, if sigma is the surface tension and delta A is the change in area, then sigma times delta A would be the work interaction due to surface tension. Another example where we have a different kind of work is due to the stretching or contraction of a spring. Let us say we have a spring of this kind. So, if we now pull this spring, we are doing work on this spring. So, the work interaction for the spring would be negative. Similarly, if this was the equilibrium position of the spring, if we push the spring from its equilibrium position, once again we are doing, the spring is resisting our pushing it and we are pushing it against its will. So, there is work interaction for the spring which is again negative. So, the spring force is given as kx, where k is the spring constant. So, the work would be kx times dx, and if we integrate it, we get half kx square as the work. So, the work in this case would be, the small amount of work would be like kx, which is the force, times the displacement dx. The dx is the displacement from the equilibrium position, either compressing it or extending it, and work would be the integral of this. Of course, k is a constant, so we can take it out. So, we get this as the work due to extension or contraction of a spring. And we note that x is displacement from its equilibrium position, unstretched equilibrium position. So, when you do not have any of these forces, wherever it would be, so from there we are moving it and we are measuring the displacement. So, these are some other forms of work, and that sort of completes our discussion of work. So, what we are also going to do is look at one or two example problems as how we would deal with this, and we will maybe solve them out, and you can look at it to get an idea of how to do the problems in the assignment. But before that, I have another little quiz for you on units, because what we see is that units are something which students who traditionally do this course have some confusion with. One of the advantages you have with an online exam is we are possibly going to tell you what the units are for each of the questions and tell you what units to give the answers in, but you should anyway know these things. So, what is MPa versus capital M? Because when we ask people to do these questions by hand and write it, so often we get either small or capital letters, people are not very careful about them. So, here is something to look at. So, a small m in the SI system of course means milli, and capital P and small a is Pascal. So, this is a millipascal, which is 10 power minus 3 Pascal, versus a megapascal, which is 10 power 6 Pascal. And in the SI unit, you would remember that when we have units named after scientists, we use a capital letter. So, capital PA is Pascal with capital P because it is named after Louis Pascal. N you would remember as Newton, defined with capital N because it is named again after Newton. So, Mn would be what is something you should think about. So, this is of course a millinewton. You should possibly pause and think about what this is. Okay, so, the small n in the SI unit refers to the prefix nano, which is 10 power minus 9. So, this would be nanometer, and you should also think about what this is. So, this of course is a Newton meter, which is the unit of either work or of torque. You should think about what this is. I do not know what it is, so it does not mean anything in our system. You should think about what this is. It's a small k, which is kilo, capital J, which is joule. So, this is a kilojoule. We do not have anything with a small j. This is a capital K and a capital J. A capital K refers to Kelvin, capital J refers to joule. So, this would be something like a Kelvin joule. Of course, what we would typically do is when we have two units of this kind, what is traditionally done is to put a dot in between, which would be the better way of representing it. Similarly, a capital K and a G would be a Kelvin and a gram. Most people when writing this are typically referring to a small k and a G, which is a kilogram. I do not know what this is either, maybe secant. So, the SI unit for time of course is just second, which is denoted by S, not by ACC, and I do not know what this is either, because a centimeter is a small c, c is in centi is small, and a second is this. So, if you want to write the plural of centimeter, if you want to write 7 centimeter, the correct way to write would just be 7 and cm. If you put a s over here, it is a centimeter second. And of course, when you write any of the any statement of this kind, you would want to put the units there, because if you say the mass of the table is 5, then it is left to the reader to fill whatever they want. So, my students usually note that in their exam answer sheets I write something like this and then mark it like this. So, because maybe the chap wanted to say it's 5 tons, but I thought it's 5 apples or potatoes, and it didn't turn out to be quite the right answer. I also have a few pointers before we go on to the problems, which we have put together based on experience of teaching this course several times. So, one of the important things is that quasi-static is something which we need to pay attention to, because if a process is quasi-static, it means it is fully resisted, so we can get full conversion of work and so on. Whereas if it is not quasi-static, that is not quite the same case. So, we need to find out whether processes are quasi-static or near equilibrium or fully resisted and so on. They are all the same thing. You need to find out whether something is a property, in which case it is exact or not, because if they are not exact, it means it depends on the path, and those are inexact things. So, you should be very clear about the difference between exact and inexact differentials. Mathematics gives us numbers. Physics tells us what the numbers may mean. For example, if I blindly write a formula W equal to PdV, the formula is something. Or if I write, for example, in the previous case W equal to mgh, this is a formula. The math tells me I can always calculate this. So, even in the case of, for example, an apple dropping, I can calculate mg into h. Okay, that is mathematics. Physics tells me what the numbers mean. So, in this case of the apple dropping, when it is not hitting anything, or the person dropping without any resistance, I can calculate mg into h, but it does not mean anything. Okay. So, it means the work if it is fully resisted. If it is not resisted, the math still gives me this number, but physically it is not of any importance to me, it does not mean anything. So, we need to understand the difference between just putting in something into the formula and getting an answer, and what that answer means. That is something which we need to keep in mind, and this is of course especially true for people who write paper exams, but it could be true for you as well. People who get low grades usually are the ones who mess up the units. So, what I usually recommend is that you always convert to SI units, do all your calculations and convert them back, because we are going to use units, for example, like the bar quite often. We are going to use kilopascals, kilowatts and so on. Some of them are 10 to the power 3, some of them are 10 to the power 5. We are going to use centimeter, which is 10 to the power minus 2 meter and so on. So, if we are not very careful, we can get pretty badly mixed up. So, these are some things to pay attention to, and we can, for those of you who are interested, I have 2 problems in the tutorial which I will explain. You can look at it, or you are free to jump on directly to the assignments without going through it. Thank you.